Okay, we'll start again. We have a ball that's attached to a string that spins in a circle. And spinning horizontally, the ball is actually horizontal. And now the maximum tension on this is 11 Newton. The question, find W max. So by the way, this force is the mv squared over r. You can also write that mrw squared, if you remember that. F centripetal is mrw squared. Two ways to write it. So when you look at the free body diagram, this is what it looks like. This is that ball there. We're looking at that picture there. If I do the x and the y axes, we have the weight down, weight, which is mass times gravity. We have the centripetal force, this one, pushing you to the right, mrw squared. And we have the tension in this direction. If the maximum tension the rope can withstand before breaking is 11, what is the maximum angular speed? Now the question here says, the key thing is an approximately horizontal circle. Well, when this is approximately horizontal circle, what does that mean? What does that mean about that rope there if it's horizontal? It's not really making any angle. If it's horizontally, it looks like this. That's where the tension is. And the weight down, and this is mw squared over r. It says assume approximately horizontal. So if I assume approximately horizontal, that means that t here, it's no longer on an angle. That t, where's my eraser, is going to be in which direction? It's going to be this way. And since you're spinning in a circle there, that means you're not moving in this direction. You're not moving left and right. That means the Tmax equals mrw max squared. This force has to equal to this. Your Tmax is 11. The mass of that is what? 0.45 kilogram. R is what? 4.7 times W squared. Can we get what W squared equal to? 11 it's 5.2, which means W is going to be the square root of that value, 2.28 rad per second. If they want to use two significant digits, W will be what? 2.3 rad per second. But that was the key, approximately horizontal. Approximately horizontal, that means the string does not make an angle. When you start spinning, it's going to make an angle. As you increase the speed, that angle starts to disappear, get less and less and less and less, and finally it's going to look like this. So let's try 2.3. Submit. Correct. You can actually close it. There were some kids out there who closed it. Now part B, it says, if the rope is shortened, became less, does the maximum angular speed found in part A increases or decrease or stay the same? If you want to watch that, go to the mall and you see these big giant circles that you put change in them, and you see the penny or whatever you drop in a nickel go in a circle, and what happens when it gets to the bottom? How fast is it moving? You can't even see it. That's how fast it moves. So when you shorten that string, it should move faster. But if you're not sure, because I've never seen those, just go ahead and pick a different value for R. Let's pick a different value for R. Let's shorten that. Let R be 3. I just picked a number less than 4.7. So 11, the tension equals the mass, 0.45, times 3, times W squared. And W will be the square root of that number, which is 2.9. So did that value increase or decrease? It actually increases. And hi mom at the end. The reason? Well, if you think about it, this has stayed the same. This one stayed the same. To get W squared, just mathematically from this equation, if you look at that equation, if you want to know why, W squared, the math says, is going to be T divided by MR from that equation, if you solve it for W squared, which means W is going to be the square root of T divided by MR. So as this number increases, what happens to this fraction? As this number increases, the whole fraction becomes larger. And if the value becomes larger, the square root of a bigger number is always bigger than the square root of a smaller number. So that's the reason why the value actually increases. That's 10.41. The key that was approximately horizontal. If they didn't say that, then we need to know what that angle is. I was watching a sniper show last night, and they were talking about the bullet coming out of it has so much kinetic energy. And it says the bullet actually leaves the gun at 2,800 feet per second and rotates at 2,000 RPM as it's coming. You're like, wow, these are large numbers. So when you look at how much kinetic energy they have in them, 1/2 mv squared, that is a massive destruction there. Here we go, we have a baseball here. If a 0.15 kilogram baseball has a radius, so we have a baseball, the mass is 0.15 kilogram, which is 150 grams, has the radius of 3.7 centimeters. Thrown with a linear speed, V has a linear speed of 43 meters per second, and angular speed, W, because you put a spin on it, 45 rad per second. How much of kinetic energy is transitional energy? Assume it's uniform solid sphere. Uniform solid sphere. Transitional, I'm sure the next question, rotational kinetic energy. This is 10.61. What is the transitional kinetic energy? It's 1/2 mv squared. We have all the values. We know what the mass. We know what V, which is 43. Now, me personally, I probably will never give you both of these, but I'll have you calculate the other one. So let's see, 0.5 times 0.15 times 43 squared. And it's 139 roughly. And if they want to use two significant digits, that's 140 joules. And I'm sure part B is rotational kinetic energy. Yep. It's 1/2. Let me leave I for now for a second. We know what W is 45 squared. We need to find what I is. Let me go back to the problem and read it slowly here. It says, assume the ball is what? Uniform solid sphere. And we're assuming it's a uniform solid sphere spinning around its center. Let me find what the inertia for that from the table in the book there. Uniform solid sphere. Where's the table? Come on. I'm almost there. Where did you go? Inertia. There's chapter 10. Okay. Either I ripped, oh, here we go. Once I ripped that page out. Here is the inertia for different shapes. Solid sphere spinning around the center. If you watch it coming out, it looks like it spins around the center. It's 2/5 mr squared. 2/5 mr squared. So let's calculate the inertia. M is what? 0.15, and R is 0.037 squared. Oh, small number. 8.2 times 10 to the power of 1, 2, 3, 4, -5. Kilogram meter squared. So 8.2 times 10 to the power of -5 times the 0.5 times the 45 squared. I got syntax error, I don't know why. 0.5 times, where's times? 45 squared. 0.083 joules. Or 8.3 times 10 to the -2 joules. Either way. That's how much kinetic energy. If you watch the picture, it throws the ball. It looks like spinning, like if there's a rod in the middle of the ball spinning around that little spot there. You can see that spot actually coming. It's not going like this on the outside of it. It's not moving like this. It's spinning around the center of it when you watch it coming at you.
I have a question.
Yes.
The first part, I'm doing exactly what you're doing with my numbers,
Mm-hmm.
and it's telling me it's not right.
Now then you're wrong.
but I just like did it on multiple calculators. I don't understand because only one of my numbers is different than yours, so it's like I just did the exact same thing.
Where'd you come up with an answer?
145, and then I put it in as 140.
150. 145.
Okay.
5 or more.
And
You
then I
add
did
1.
that, and I said, no, I don't know.
Yep.
Maybe I didn't. Oh, I did. Never mind. I did 146 by accident. That makes sense.
It's two significant digits.
I
Yep.
thought it said
Yep.
3.
Two significant digits. See how my answer is? I'm always a wise guy. We have a hoop here, 1058. I'm assuming I only didn't finish reading. Let me look quickly here and see if that's the case. Is there an incline? It doesn't say there's like a little incline there. I assume it was. I don't see it actually. So, okay. Change it. 1058. There's no incline. We have a hoop. 1.05 kilogram, the mass. It's rolling. It's moving in this direction. Has a radius of 10 centimeters. Rolls without slipping, good. If the linear speed v equals 1.84 meters per second, find the translational kinetic energy, rotational kinetic energy, and the total kinetic energy of rolling hoop. How much is translational? KT, translational, 1/2 mv squared, straightforward. We know the mass, we know V, nothing fancy. 1/2, 1.05 times 1.84 squared. How? 1.8. 3 significant digit, 1.78. So the transitional 1.78, comma, where's the comma? Somewhere there's a comma. The rotational kinetic energy, 1/2 I W squared. I need to get what I is. It's a ring here, it's a loop there. An I for a ring spinning around the center is mr squared. From the chart, 1.05, R is 0.1 squared, 0.0105, I think. Let me just see. 1.05 times 0.1 squared, 0.0105. Kilogram meter squared. W, we don't know what W. V equals R times W. We know what V. We know what R. Can we find W? W is 18.4 rad per second. So the rotational kinetic energy is 1/2 I 0.0105 times W, which is 18.4 squared. And again, 1.78 joules. And what is the total kinetic energy? It's the sum of them. if I carry all the digits, 3.55, if I carry all the digits. But if I use 1.78, 3.56. They said their number was they gave me the credit, this 1.81, 1.81. They probably carry different significant digits than me. But I got the points. It's 1.81, 1.81, 3.62. I thought I carried all the digits there. Oh, I know why. For mass, it was 1.07. I put 1.05. That's why. My number was a hair off. Their mass was 1.07. What's the next one? Okay. Here we go. A 1.6 kilogram solid sphere. So this is actually coming down here. This is a solid sphere. The mass is 1.6 kilogram. Has a radius r equals 0.20, is released from rest, initial velocity is 0, along a ramp, allowed to roll without slipping. The ramp has 0.85 meter height, 0.85 meter high. And here's the sphere on the bottom, and it's 6 meters long. Doesn't really matter how long. When the sphere reaches the bottom of the ramp, what is the total kinetic energy? It didn't say which kinetic energy, it says total kinetic energy. Okay. This is 1076. Let's look at the top. We have potential energy, kinetic energy due to rotation, and kinetic energy due to translation. This is the total energy. Now, the potential energy is the mass, gravity times height. 1.6, gravity 9.8, and the height is 0.85. Kinetic energy, 1/2 I times W squared. W is 0. Initial velocity is 0. It wasn't moving, wasn't spinning. It was at rest. Plus kinetic energy, 1/2 the mass, times the velocity squared. So the top, what's the E total equal to? The total energy in it. .328 joules. This is the top. Let's look at the bottom. the total energy at the bottom. It is the potential energy, kinetic energy due to rotation, kinetic energy due to translation. I'm using this as reference, the height here as reference. That's why I use for the height 0.85. So the potential energy is 0 because the height is 0. The kinetic energy is 1/2 I W squared. I don't know what I or W yet. The kinetic energy to translation 1/2 M V squared. The question, what is the kinetic energy at the bottom? Well, that's easy to answer, right? If they're looking for the kinetic energy at the bottom, they're looking for these two numbers. That's your kinetic energy at the bottom, right? So the total is going to be, I don't have to know what the value is. It's this value, Kr plus Kt. It's this plus this. There's no potential energy. Maybe for part B, I need to know other stuff. But that's what the total energy at the bottom is. Just kinetic energy. And you want that to equal to this, right? Conservation of energy. So the kinetic energy at the bottom should equal 13.328 joules. And if they want two significant digits, that's 13 joules. Submit. Correct. But now the next question is probably what's the speed when it reaches the bottom? Or what is the rotational kinetic energy? I need to know what W is. What is the translation of what's this value equal to? Now they want to separate them. They want to know what each one is. So I have to know what V or W is. One of them. Because if I know one, I know the other. I know V equals R times W. So if I go back to this equation, if I go back to that equation, because right now I have two unknowns in it. I have E at the bottom here is equal to 1/2 I times W squared plus 1/2 M. Instead of V, let me put RW here. And I know R, I know M, except I don't know what I is. For a sphere, what was I? For a sphere, it's 2/5 mr squared. So let's calculate what I is. 2/5. The mass, what's the mass? 1.6. And what was R? 0.2 meters? .0256. So here we go. 1/2 I, which is 0.0256 times W squared plus 1/2 the mass, which is 1.6 times R, 0.2 squared times W squared. .0128 W squared plus 0.032 W squared 0.0448 W squared. That's the total at the bottom. And we know we have conservation of energy. The top equals the bottom. At the top, we said it was what? 13.328. The bottom, 0.0448 W squared. Can we get what W squared equals to? This is 297.5, which means W is going to be, take the square root of that number, 17.25 or 17.2. Now I can answer all the questions. What do you want to know? How much kinetic energy due to rotation? Once I have that, kinetic energy due to rotation is 1/2 I W squared. I know every one of these. 1/2 I 0.0256. W squared is 297.5, right? Don't square it, that's the squared. W squared equals 297.5. I already have it there. .81 joules. Two significant digits. 3.8 joules, two significant digits. They want two significant, says use two significant. V equals R times W. We know what W is. V equals 0.2 times 17.2 3.44. Kinetic energy translation is 1/2 mv squared. One half, we know what the mass, 1.6, we know what V, 3.44 squared. And two significant digit, that'll be 9.5 joules. .466688, that's 9.5 joules. So once we have W or V, we know what the other one is. You can either solve for W or V. Once you have it, then you set them equal to each other. You know the kinetic and the translational and the rotational kinetic energy, all three of them. The last one,
how did you do the K total?
add them.
Okay.
Yep, add the two numbers. Kinetic energy rotational plus kinetic energy translational.
So it's the same, my rotation was wrong.
Huh? For part A, actually, that's, you don't even have to calculate them at that time. But if you calculate them now, you can add them. Add the two numbers, the 3.8 and the 9.5. What's that, 13.3? Yep. This is the 10.66, the last one. We have a block of mass 1.9 kilogram. I think we did this last time too. 1.9 kilogram is attached. It's moving upward with the velocity v. This one spins. The pulley spins. R equals 8.9 centimeters for the pulley. Initially this was spinning at W. They're not telling us what W, but they say, you know what? Initially when you hook that weight to it, this one moved up with the speed of 0.38 meters per second. And what's going to happen is that pulley is going to spin, and now this is going to move up there, the 1.9 kilogram, and has a velocity of 0. Stop moving. Well, if V equals 0, that means W is equal to 0. This is stop spinning. And if I use this as reference, probably the question, how high is it going to go? Is that what the question is? Oh, no, we're given the height. They changed the question here. It moved up 6.8 meters. Can you find what the inertia is for the pulley? We know it moved up 6.8 meters. That's a decent amount. Oh, 6.8 centimeters, my mistake. I'm saying, wow, that's a decent amount. 6.8 centimeters, not meters. This system here is the before. Bless you. And this is the after. Let's call this the mass of the pulley. And what should we call this? The mass of what? H hanging? Whatever we hang in there. So you know which one's which. So let's look at it. This is actually not changing, so potential energy for this pulley does not change, so I don't even have to deal with it. This one's spinning, it has a rotational kinetic energy. So let's look at the energy before. This has a kinetic energy due to rotation, which is 1/2 I W squared. Plus, that's it. That's the only energy this one has. Spins. It's not moving up and down. This one is moving up and down, has kinetic energy. It's 1/2 the mass, the hanging mass times the velocity squared. This mass times the velocity is moving up. Plus the potential energy, which is the mass, the hanging mass times gravity, which is 9.8 times the height, which is 0, if I use this as reference. Plug in the values. I'm looking for I. We don't know what W is, but wait a minute, we know what V is, right? V equals R times W. V is 0.38. R is what? 0.089 meters. That's in centimeters. You divide it by 100 times W. What's W? .27. So I times 4.27 squared plus 1/2 times the hanging mass, which is 1.9, times the velocity squared, which is 0.38 squared, and the last one is 0. 9.12 times I plus this number is 0.137 plus the 0. You can't really add them. This have I, the other one doesn't. And that's the total for before. How much energy before? Let's look at the energy after. E after. This one moved up. So the kinetic energy due to rotation, well, that thing never moved the height of it, the pulley there. It's 1/2 I, but W is 0. The weight moved up, but now it's no longer moving. It's 1/2 the mass, which is 1.9, times the velocity squared, which is 0 squared. Plus the potential energy, this one moved up, which is 1.9, gravity 9.8, times the height, which is 0.068 meters. We have 1.27. So what's the sum here? 1.27. What do we know about the sum of the energy before and after? They should be what? And they're supposed to be equal to each other? E before should equal E after. E before 0.137 plus 9.12 I equals 1.27. Bless you. And now solve for I. Move this to this side. 1.27 minus 0.137. 1.13 I equals 0.124 kilogram meter squared. If you want two significant digits, you can write that 0.12 It says using two significant digits. That's what the inertia of that pulley is going to be.